Okay, so the next in the series of things you can do with two-level systems that are relevant in chemistry is going to be looking at coupled molecular vibrations. Most molecules have more than one vibrational mode, and most of them are coupled to each other, and that coupling can have consequences on, for example, the vibrational structure, meaning like what the spacing of the energy levels is, or the relative transition moments that reflects maybe the symmetry, as well as dynamical properties like how energy relaxes or transfers amongst the vibrational modes. And some of that can be measured with experiment, and there's a belief or an expectation that some of that has to do with actual chemical reactivity, although to be fair, it's actually quite tricky to pinpoint exactly when a particular vibrational mode is related to an actual chemical reaction. People are trying to do that, figure it out, because we expect it to be the case, but it's hard to actually observe in experiments. Okay, so what's going to be our sort of Gedanken system? For me, I'm going to pick carbon dioxide. You could pick anything, and later when we formulate this, you'll see you can really think of any vibrational system like this. I'm picking this because hopefully this is one of those classic problems that everybody's already seen before. Usually when you learn about vibrational spectroscopy, you learn about the selection rules, and one of those selection rules is that to have an infrared transition, there needs to be a change in the dipole moment when you distort the molecule along whatever coordinate it is you think is going to be the vibrational mode. So for example, with carbon dioxide, one of the vibrational normal modes, we'll talk more about normal modes later, it's going to pop out when we do it here, but it won't be the way that you would get to it if you treated the problem like a true vibrational problem, like using something called a Hessian matrix. But anyway, one of the normal modes is the symmetric stretching of the two oxygen atoms, and the other one is the anti-symmetric stretching, which has the oxygens moving sort of together but against the carbon. Now, of course, there's a bend as well, but the bend is not going to be treatable with the coordinate system that we use. Right? So for this consideration, we're just going to be looking at thinking about one vibrational mode of carbonyl that's on the, let's say, right-hand side, and another one that's over here. We're going to think of them as basically being two coupled harmonic or two coupled oscillators, and I'll show you how they can be coupled and stay harmonic, or they can be coupled and become anharmonic, as we know that they of course are in real life. And so just like before, where we had A and B of the two-level systems, or we had site 1, 2, 3, 4, whatever for our Huckel model, here we're just going to pick 1 and 2. All right, for our coordinates. So the coordinate means when you see Q1, for example, Q1 is going to be displacement of the oxygen on the right away from its equilibrium position. That's the Q. And Q2 will be displacement of the oxygen from its nuclear position. So positive Q1 is this way, and positive Q2 is that direction. They're in opposite directions. Right? So we're always considering like the 0 to be the carbon in the middle, and then this is Q1, and this is Q1 positive this way, Q2 is positive in that way. You could do everything exactly backwards, and then all the numbers would be just with a minus sign somewhere. All right, so we have Q1 and Q2, and we're going to figure out a way to write down the Hamiltonian, okay? And then we're going to add a coupling between the two modes. And when we do that, just like we saw in the case of a two-level system, they will couple and they will split in energy into a symmetric and anti-symmetric stretch. The nature of the coupling now is going to be due to the influence of distorting one vibration and or one coordinate, and how that makes the vibrational potential on the other side change. That's anharmonic coupling, which we'll discuss. All right. So let me show you how you set this problem up. First thing to remember is that we have, our normal Hamiltonian, right? Our normal, the Hamiltonian for the two individual harmonic oscillators, which we'll call H1 plus H2, right? And we have the solved eigenproblem for each of those two things. I'll write that up here. Let me get some space. So H1, for example, operating on N will give me back, let's call it E1 to make it sort of simple, yes, I'm just going to make the energies, let's just be general. Let's be general. So H, this would be then 1/2 mu, the mu's are the same, omega 1 squared, but you can call them mu1 if you want, Q1 squared plus 1/2, this is the potential, mu 2 omega 2 squared Q2. To make the Hamiltonian, it would just be P squared, P1 squared over 2 mu for one, and P2 squared over 2 mu for the other dimension. Okay, so that's the Hamiltonian, that's the potential. You'll have an energy, E1, let's call it like that, right? That's the solved eigenvalue problem. H2 operating on whatever it operates on will give us the 2 and n. All right. So what we do is we make a basis, right? We know the basis is going to be each vector from one Hilbert space, from one Hamiltonian, the eigenvectors of one Hamiltonian, paired with an eigenvector of the other Hilbert space. Right? That's what we mean by tensor product vectors. And we can write those down in the same notation that we've been doing all along, NM, which is just to be understood. Take one vector from Hilbert space 1 and combine it with one vector from Hilbert space 2. And so there will be many of these. Of course, there'll be an infinite number of those. So for example, 0, 0, 0, 1, 1, 0, 1, 1, and so on. It doesn't stop because this is not two-level systems anymore, right? What I'm going to show you is how we can write it out for a very large case, which is not a two-level system, but then we'll see the same thing happen where a little subset of the matrix is going to look exactly like what we had when we had coupled two-level systems. All right, let's see how that works. So we have this infinite, of course, dimensional Hilbert space made up of the tensor product of the individual ones. We could, of course, enumerate these, like I said before, 1, 2, 3, 4, 5, and so on, instead of writing them in this way, but then we would lose contact with where they came from originally. Hopefully it's reasonably clear that this is the same linear combination of these Hamiltonians. So if I operate with H on this basis vector, I'm going to get H1 plus H2, right, on the basis vector. Whoops, that's ugly. There we go. The H1 talks to N, the H2 talks to M, and so then, of course, we'll have E1N plus E2M and M. All right, that's what you expected, hopefully. Now, we can write down what the energy levels look like. If we assume the two harmonic oscillators are the same, which is the most obvious choice here because the two carbonyls are exactly the same. All right, so then we're going to have a ground state that corresponds to the ground state of both. That would be the 0, 0 situation. Then we have one excitation of mode 1 and no excitations of mode 2 and the vice versa. So it'll give us a doubly degenerate 0, 1 and 1, 0. Okay. Now, how can we have two quanta of excitation? Well, there's three different ways to do that. You can either have 0, 2, 0, 2 as just 2, 0, but also 1, 1. They all have the same energy. So you'll get 3. All right, and these energies are still spaced by h bar omega. We only have one omega now if these two are the same. All right? So, and then so on. And the degeneracy grows. There's a little recursion formula you can figure out for that. That's not super important. The point is it gets bigger as you go up. All right? Now what we're going to see is if we include coupling in here, it's going to split these energies apart. Right? Now it's going to split all the energies apart. But what we're going to do is we're going to see that the first excited state manifold follows the same pattern that we saw with the two coupled two-level systems, n-coupled two-level systems, and the example of the Huckel as an application of all of this. Okay, so how do we do this? What we're going to do is we're going to figure out what kind of coupling we want to include, right? And so now we have to think not so much like we're doing math, we have to think like we're doing science. So the coupling this is something that you can actually do by yourself in different ways. Right? So what we want to do is we want to imagine that we have our molecule, right? And just remind ourselves what these potentials mean, what these potential energy functions mean. They mean if I have, so I have my 0 position here, Q1 is equal to 0. If I pull the oxygen out, the energy will go up, of course. If I push the oxygen in, the energy will go up also. Now, of course, what it's really going to do is going to give me a kind of a molecular bonding potential that looks like what you expect, where it will be extremely sharp there, then it will go down to a minimum, and then eventually it will pull apart. So that's how the right-hand side of this would look. For the left-hand side, it's exactly the same, but it's the mirror image. I push it in, energy goes up because of the repulsion. As I pull it apart, eventually it flattens out again. So we'll have a potential energy function that looks something like this. It goes down and then up and then like that. And these two would be exactly the same. I'm just not perfect at drawing them. So what I want you to think about now is how can I think about the two couplings, the two interactions between these two vibrations, or these two modes, or these three atoms. And so the thing to do in your mind is to imagine that when you stretch this carbonyl out, for example, let's imagine we take it from 0 and we stretch it out by that much. What is that going to do? That's going to change the way the electrons distribute themselves. So we can do this in our mind as a Born-Oppenheimer step, right? We just move the oxygen farther away. For example, we could go into Spartan. We could go into Spartan right now and do this. Maybe I will. What you do is you take your carbon dioxide, you optimize the geometry, and then you simply set the geometry of the distance between these two atoms to be a little bigger. Maybe 1/100th of an angstrom or a 20th of an angstrom, something like that, some small amount. Then you calculate the energy, okay? And then what you do is you distort this one, move it out a little bit, calculate the energy, and then move it in a little bit and calculate that energy. All right? And what we're going to see is the way that this atom displacement influences the change in energy over here, which you could, if it was a classical problem, we would call it the force. Here we're going to stick to talking about potential energy, is that we would expect that the potential energy function will change depending on what happens on the other side of the molecule with its distortion. Right? Now, how do you figure out what to do? So you could either do a whole sequence of positions. So for my cartoon, I'm going to do a whole sequence of positions. But for the calculation that you were doing, you could do 3 points would be enough. All right? So what we're going to do is we're going to imagine that when the oxygen is at 0, I'm going to call that the solid line. So when Q2 is equal to 0, we have the solid line. All right, so let's call that Q2 equals 0. This is Q1. So we're basically plotting like a two-dimensional surface, but on one graph. It's easier to see that way. Now what we're going to do is actually distort the other side and move this out to some other amount, some number bigger than 0. Now I don't remember in this molecule what ends up happening. If pulling this out transfers some electron density into the antibonding orbital over here, then what you would expect to happen is you'd expect this bond essentially to get weaker. And if it got weaker, that would make the frequency go down. It could also be that when you pull out this oxygen, somehow electron density gets transferred into more bonding orbitals. Right? If that's the case, then you'd expect the frequency to go up because the bond would get stronger. Well, we don't know which it is necessarily from this picture, so I'm not going to pretend like I know. I can calculate it, but I don't know right now. So what I'm going to do is I'm going to pretend that the frequency over here gets weaker, that pulling this out, some electron density maybe transfers and makes it less bonding. Or maybe some bonding electron density would somehow leak over here. That seems less likely to me, but whatever. The idea is you can tolerate all possibilities because you can calculate them. So now we have Q2, let's say greater than 0. All right? So what you see that's happened is the frequency that you would get, the frequency comes from this curvature of the potential. The mass isn't changing. The only thing that's left to change is the frequency, and the frequency has in it the force constant. So this would be Q2 greater than 0. Now I can imagine also pushing it in a little bit. push it in a little bit. I do it again. So now Q2 is less than 0. And maybe I'll get yet another curve that might look something like this. Right? And I have to write Q2 less than 0. So what you would do then is you would basically do something like a kind of a fit, right? You would take this parabola, fit it to a parabola, take this data, fit it to a parabola, and maybe the way I've drawn it here, you would do something like plot it against Q2, right? Q2 is here. Q2 equals 0. That's whatever the initial frequency was. It's there. Then as I increase Q2 and make it greater than 0, the frequency went down. Right? So I got maybe a point over here. If I'm fitting this parabola, it went down. And then when I make Q2 less than 0, which is this one here, the frequency went up. So that would look like this. If I connect the dots, what do I end up with? I have a linear dependence, and if you make this change in frequency, this change in displacement small enough, it'll certainly be linear like this. I will have a frequency of along Q1 that's linearly dependent on the displacement along Q2. So what is this vertical axis? I guess I didn't write that down. This is, let's say, omega 1 that you would extract from the fitting to a parabola. Okay, so what that means is this is a term in my potential energy function that would look like Q1 squared, because that's the parabola, right? Whose frequency was dependent on Q2 linearly, all right? Times some weighting factor for this, right? Times some magnitude. Okay, so this is an example where we're changing the frequency because of distorting or displacing another dimension along another dimension. Right? So we call this a kind of anharmonic coupling. Why is it anharmonic? It looks like it's harmonic. The reason it's anharmonic is because the overall power here is 3 powers of distance. So that makes it not second order. Okay, so it's an effective frequency that depends on the displacement. The terminology in some literature that certainly in some of my community members use would be to use a beta 112 for this. The order of these doesn't matter. It's just that you see the repeated index means that it's the one that has the 2 powers. You could imagine just writing Q1, Q1, Q2. That would be mathematically equivalent to this. All right, so this is a way of introducing anharmonicity into a potential energy function. Now what I'm going to do is I'm going to show you an even simpler way to do this, all right, or a simpler way to add coupling between the 2 states. This is absolutely anharmonic coupling. You can imagine another term that would be the sort of reverse of all of this. So beta 122, so that would look like Q1, Q2 squared. Right, so you distort the other one and you see that now this molecule is completely symmetric, so you'd expect these 2 to be exactly the same, these magnitudes to be the same, but these are different operators, right, who need both of those in the Hamiltonian to make them work. All right, so these are what we call off-diagonal anharmonicities. And they're off-diagonal simply because if you imagine sort of thinking of beta a little bit like a tensor or something like that, these are the ones that are not on the diagonal of that tensor. What about just the natural anharmonicity of Q1 by itself, right? We drew the diagram at the beginning, had a potential energy that went like that. All right, so you can do that too. You can have beta 111, which is beta 1 times Q1 cubed. Right, and you can of course do the same thing, beta 222 times Q2 cubed. In this molecule, you'd expect these numbers to be the same as well because they're the same molecule, same kind of bond. Right? If it was OCN or something, then you would expect maybe it would be different. All right, so these are the lowest order anharmonic terms that you can have in a 2-dimensional harmonic oscillator, or 2-dimensional oscillator, sorry. All right, And we can think about those. It turns out those are a little bit complicated, so I'm going to put them aside, and we're going to consider a slightly simpler kind of coupling that would be one that would lead to an effect that you would see experimentally, but by doing simple linear IR spectroscopy, you would never be able to distinguish it from this much more complicated potential energy function. And that's one of the things also to do to motivate. Why do we do nonlinear optical spectroscopy? And one of the reasons is because it allows us to know more about the Hamiltonian, because we go up higher in the energy level structure, and that allows us to see more terms in the potential energy function. All right, so one trick I can do, certainly I can write these down. You see this, of course, as a Taylor series, right? So I'm making a Taylor series. I'm just stopping at the third order. Maybe I needed to put the fourth order, and whatever, I can keep making higher order corrections. There's a little bit of a theorem, which is that the highest order Taylor series that you have is discernible from an experiment whose field power is also that order. So if we do third order spectroscopy, we'll learn about that as the course goes on, which is like pump probe or 2D-IR. We can determine the third order parameters. We can't tell if there's a fourth order parameter. We need to go to another higher level to figure that out. So I don't actually know if that's a theorem or a practicality. It can maybe, we take it for granted, but maybe someone proved it. Maybe it's just something that happens practically. It doesn't matter too much. We don't really, it's not super common to actually fit these potential energy terms to experimental data, but some people do. We've done it for sure, but that doesn't mean that it's very common. Okay, so what I'm going to do here is I'm going to make the coupling even simpler, which is to simply have a linear term. Now, what does a linear term do to a potential energy function? Here's a parabola. Well, if I add a linear term, for example, something like this, make it simple and have it go through 0, then it's actually relatively straightforward to see that what's going to happen is that the potential will shift. Right? And so what you'll end up with is a potential that basically just moves. The important thing is the curvature of the potential stays the same. So if it was omega here, it's omega here, but there's an offset. Right? In other words, adding a linear term does not make it anharmonic. But what it does allow us to do is have coupling between the different vibrational modes. It's the simplest kind of coupling you can have. So we're going to call this V, and I'll just call it bilinear, BL. And that's going to be a number. We just need to have some number, alpha 1, 2. You can see alpha is distinct from beta. And then we'll call that Q1 times Q2. So from a mathematical point of view, this is the simplest kind of coupling we can have that mixes the 2 degrees of freedom of Q1 and Q2. Before they were just separated like this. All right, and so what we're going to do is work out the matrix elements for the Q1 times Q2 potential, put it back into the Hamiltonian that we already have in the diagonal form over here, and then look at the form of the matrix that we have when we do this. All right, and we're going to use our super powerful tools of the creation and annihilation operators to figure out what these matrix elements are. So I can do a few of them right away. Let's not worry so much about the alpha 1, 2. That's certainly going to be something that we need to put in at the end, the strength of this effect. So what is Q1 and Q2? So remember what we have. I'm going to use the capital Q notation. We can always put it back into the units that we like by remembering how we transform from little q to big Q. So I'm going to write down 1 over the square root of 2. A1, this is annihilation operator for the 1 dimension. So it's like exciting, or in this case, de-exciting along Q1, plus A1 dagger, and then A2 plus A2 dagger. All right, so this notation is new. We did not have this notation before, right? We used A and A dagger, but we didn't talk about different dimensions. So now what we're doing is we're just keeping track. Now remember that we had a commutator, right? We had a commutator A with A dagger, which turned out to be very powerful for doing manipulations. Now what we're doing is we're simply going to augment this with the fact that there's different dimensions. So we'll have a j, a k dagger, and then it's a cute, fun little exercise to prove that this is equal to delta jk. If these two labels are the same, if it's the same dimension, then we have a 1, but they commute if they're on the different dimensions. Right? You can do that by converting them back to Q and P, and it's a page, but it's not conceptually that challenging. All right, so what did I do wrong? I forgot the other square root of 2. So we have this thing squared. Very good. Now this doesn't matter either, but we have to keep it along just to make sure that we don't screw up, especially when we're adding it to the other terms that we have, which we'll know all about these factors. All right, so what does this look like? This looks like 1/2 times all the stuff that we're about to do. A1, A2, A1, A2 dagger. Now these commute, so if you don't like the ordering, you can order it however you want. And then A1 dagger, A2 dagger. All right, and then we're thinking ahead what this is going to do when we do a matrix element, right? What we're going to do is we're going to go up and then up again, and then we're going to come on the other side with our, bra, and that has to match with what we got. So this is going to mean 1 state higher for mode 2, 1 state higher for mode 1, and we need to be there to match those two, so like that on both of them. This is going to take the mode 2 quantum number, lower it by 1. This is going to make the mode 1 quantum number, raise it by 1. This is going to do the opposite of that. This is going to look a lot like the coupling that we had for our 2-level system, which is why this isomorphism exists. Here we're going to take the Q2 quantum number down by 1. Here we take the Q1 down by 1, and then we have to match them up. So you can see where the delta functions are going to be. There will be no terms where both quantum numbers are the same, right? And there will be no terms where any one of the quantum numbers is the same, right? So only cases where they both change, namely this one here and this one here, or where one changes and the other one goes up and the other one goes down, they flip-flop basically. So here are your flip-flops and here are your up, up, down, down. That helps you. You could write the matrix down immediately if you just thought of that, but let's go through it a little bit slower to actually write out what those matrix elements are.